Hi everyone, welcome to this YouTube channel. We're about to look at NECO Physics July 2023 final solution to NECO Physics July 2023. If you are not subscribed to this channel, subscribe. Do well to subscribe to the channel, and you can also invite friends to subscribe to the channel. So looking at the final solution to the practical questions in NECO Physics Practical. We are starting out with number 3. Number 3 is a question under electricity. We can see the resistance bus given to us there, connected to a bulb, which is in parallel to resistance bus. Have the ammeter for measuring current. Have the key or the switch. We have the battery, and then we have the rheostat or the variable resistor. Then that the connection given to us. We have this question which says you are provided with a resistance bus, touch light bulb, ammeter, key, rheostat, battery, and conducting wires. Using the diagram above as a guide, carry out the following instructions. Number 1, connect the circuit as shown in the diagram above. Number 2, close the key and adjust the rheostat until the bulb glows. Do not adjust the rheostat again throughout the experiment. Open the key and set the rheostat, so the resistance bus R to be equal to 1 ohm. IV, close the key, read and record the ammeter I, that the current of the value of the ammeter. Also record the resistance R. Evaluate V evaluate R raised to power 1, that R inverse. Then VI, repeat the procedure for R equal to 2, 3, 4, and 5 ohms, respectively. In each case, read and record the ammeter readings I, record R, and evaluate and record R inverse. VII, tabulate your readings. Then VIII, plot the graph of I, that is current, on the vertical axis, and R inverse on the horizontal axis, starting both graphs from the origin, both axes from the origin, 0, 0. Then IS, determine the slope S of the graph and the intercept C on the vertical axis. S, evaluate K equal to S over K. Okay, number S, evaluate K equal to S over C. You know that S is the slope and C is the intercept on vertical axis. Then SI, state 2 precautions taken to ensure accuracy. BI, which is greater in value between the EMF of a cell and the potential difference across a load connected to a cell? Give a reason for your answer. BII, two resistors of resistances 2 ohms and 4 ohms are connected in series to a dry cell of EMF 1.5 volts and internal resistance 0.5 ohm. Calculate the current passing through the circuit. So let's go to the solutions to this problem. So these are table of value for number 3, electricity. The question we just read out now. The experiment was conducted using 2 dry cells. That is, each of them is 1.5 volts each times 2, giving us total EMF of 3 volts. So according to the instruction, you can do the experiment with 2 dry cells, or you can still use an accumulator of 2 volts. But in this one, we're using 2 dry cells. If you use accumulator of 2 volts, you're going to have different reading from what I'm going to read out now. Now, going to the table, we have the serial number, the first column. Serial number indicates how many times the payment was done: 1, 2, 3, 4, and 5. Have the resistances from the resistance bus: 1 ohm, according to the equation, 2 ohm, 3 ohm, 4 ohm, and then 5 ohms, all written to 4 significant figures. We now have the inverse of resistance we're out to calculate. The unit of resistance is ohm. So the inverse will now be per ohm. So inverse of 1 is 1. Inverse of 2 is 0.5. Inverse of 3 is 0.333 continuous. Inverse of 4 is 0.25. Inverse of 5 is 0.2. All values to 4 SF. Then current, when the resistance was fixed at 1 ohm, current flowing was recorded as 0.75 ohm. When the resistance was fixed at 2 ohm, current obtained was 0.600 ampere. When the resistance was fixed at 3 ohms, current obtained was 0.500 ampere. When the resistance was fixed at 4 ohms, current obtained was 0.4300. Resistance was fixed at 5 ohms, then current obtained was 0.375 ohms. So you can once again go through the table and see there's no error. It's a perfect experiment. Using 2 dry cells, each of EMF 1.5 volts. Now, we'll now go to the graph. We are out to plot the graph of current on the vertical axis against inverse of resistance on the horizontal axis. Current on the vertical axis against inverse of resistance on the horizontal axis. The higher value of current is 0.75, as you can see there. The low value is 0.375. The higher value of inverse resistance is 1.0 ohms. The least value is 0.20 ohms. We'll now go to the graph. So we have our graph there. Graph of current on the vertical axis against inverse of resistance on the horizontal axis. Let's look at the scale we chose. As we said, the highest value of current is 0.75 ampere, while the least value of current is 0.375 ampere. Let's look at the vertical axis. We'll choose 0. Look at it very well. We chose 0.1. 0.1 to represent 0.1 to represent 2 units. 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, and 0.8 on the vertical axis. On the horizontal axis, which is the arrow inverse axis, they look at the scale we took. We took 0.2 to represent 2 cm, 0.2, 0.4, 0.6, 0.8, 1.0, and so on. For you to plot the graph, you need to understand the scale very well. Now let's look at the scale. What does each line represent? So as I said, for the vertical axis or I-axis, the scale chosen is 2 cm. 2 cm to represent 0.1 ampere. Then what does one line represent? One line is going to be 0.1 divided by 10. Since there are 10 lines in a bus, so divide 0.1 by 10. You now have 0.1 divided by 10. That will give you 0.01 to know what one line represents. So you can easily read off your scale. Then going to the arrow axis, horizontal axis, we have 2 cm represents 0.2 unit. As you can see it here, 2 cm, this is 0.2 value here. That is 0.2. So let me go come down again. Okay, 0.2 as in a bus. So 10 lines in a bus. So know what one line represents. We'll divide 0.2 by 10 as we did on the paper. So one line is 0.2 by 10, giving us 0.02 unit. So after plotting the graph, we obtain a straight line graph. As you can see, a straight line graph that did not start from the origin. It's a good graph or a good experiment, whereby you can see we have the points. Out of the 5 points, we have the points. The first point here, 1. Second point, 2. Third point, 3. Fourth point, 4. And then fifth point, 5. Out of the 5 points, 4 points enter the line, while only 1 point fell out of the line. So it's a good experiment. Question IS says we should find the slope. Okay, determine the slope S of the graph and the intercept C on the vertical axis. So let's go to the slope. So going to the graph, have to choose 2 points to find slope of the graph. So we'll do a triangle from this point. We'll come down to this point to take our slope, which should be the change on the I-axis, all over the change on the R inverse axis. So we'll look at the calculation. So we have our slope, change on the current axis, which is vertical axis, all over change on the horizontal axis, which is the arrow inverse axis. We now have 0.75 minus 0.5 all over 1 minus 0.33. That gives us 0.25 amperes all over 0.67 ohms. Okay, ohms. Then dividing, we had our slope as 0.00373 volts. That is our slope. So you can see from the point we took our slope, if you take this point to the vertical axis, the place will give you 0.75. Then from this point, bring it to the vertical axis, that will give you 0.5. Then coming down from this point, where I have the ruler, from this point, coming down, we're going to meet the value of one whole number. That is the value there. One whole number. That the intercept on the horizontal axis. Then moving up again, we'll now trace from this point down to get the coordinate. I'm going to get from this point, where I have it to go to the horizontal axis. We're now going to get around 0.33. So that is what we had. This 0.33 75 minus 0.5 all over 1 minus 0.33, and then we got our slope as 0.00373 volts as at the slope of the graph. The next question is that we have to find the intercept on the vertical axis, which they call C. The intercept on the vertical axis is going to be 0.340 amperes as read from the graph. So you can see the vertical axis, the intercept here. Look at where it is. And each reading on the vertical axis is 0.1 from our scale. So Z is 0.3, 3.1, 3.2, 3.3, and then approximately 0.34. So the intercept is 0.34 amperes on the vertical axis. So further, we are asked to evaluate Ks over C, that is the slope over the intercept, and we got 0.0110 ohms from the evaluation of a slope over the intercept. We have 0.011 ohms. The next question is on precautions taken to ensure accuracy. There are many precautions you can take. We have two there. The first says, I ensure that I avoided error due to parallels while taking readings from the ammeter. Number two, I ensure that I made tight connections in the circuit. You can also say that I ensure that I remove the plug from the resistance bus when I'm not taking reading to avoid the battery from running down. We now go to number 3B, which says, which is greater in value between the EMF of a cell and the potential difference across a load connected to a cell? Give a reason for your answer. Solution: the EMF of the cell is always greater than the potential difference because of the potential drop, or I can call it the lost volts, across the cell caused by its low internal resistance. Then the last question, number 3, says two resistors of resistances 2 ohms and 4 ohms are connected in series to a dry cell of EMF 1.5 volts and internal resistance 0.5 ohm. Calculate the current passing through the circuit. So let's go to the solution. Solution: since the resistors are connected in series, we'll find the net. We're going to be R1 plus R2, 2 plus 4, giving us 6 ohms. The EMF of the battery is 1.5 volts. The internal resistance is 0.5 ohms. Use the formula for current flowing through the circuit, which gives I current equal to EMF all over external resistance plus internal resistance. Substituting, EMF is 1.5. Total external resistance is 6 ohms, as you can see there. Then plus internal 0.5. We now have 1.5 over 6.5. Dividing, we have 0.231 amperes to 3 significant figures. So let's go to question number 1. So question number 1 is on mechanics, which involves spiral spring. You can see the diagram. A spiral spring hung there. Then we have a meter rule suspended close to the spiral spring. We have a pointer, which is joined to the spiral spring by means of a plasticine. We have a mass hanger hanging down there. We have the length, LO. The length represents the length of the spiral spring when it's carrying a mass hanger hung on it. Then we have the mass hanger, of course, and then the whole setup is given to us there. So this is the schematic diagram of number 1 question. Then the question says you're provided with a rotor stand, spiral spring, plasticine, pointer, masses, stopwatch, and mass hanger. Using the diagram above as a guide, carry out the following exercises. 1. Clamp the meter rule vertically. 2. Suspend the meter rule vertically. Number 3. Suspend a mass hanger on the free end or the spiral spring. Number 1 is, let's go back, the error somewhere. Number 1 says clamp the meter rule vertically. Number 2 should be suspend the spiral spring, not meter rule, suspend the spiral spring vertically. Number 3, suspend a mass hanger on the free end of the spiral spring. Number 4, suspend the pointer horizontally on the free end of the spiral spring using the plasticine. Number 5, determine and record the distance LO. So as I explained before, so this is the LO, this is the meter rule suspended vertically. This is the spring, the second command, suspend the spring vertically, and then suspend a mass hanger on it, on the free end. Then find the distance from this end to the end of the spiral spring when the mass hanger is lying on it, and call that distance LO. Number 5 or 6, add mass M equal to 50 gram on the hanger. Then VII, determine and record the new distance L of the pointer and evaluate E is extension given by L minus LO. Remember that LO is the mass, the length of the spiral spring when the mass hanger alone is hanging on it, while ordinary L is the length of the mass hanger when you start slotting masses on it, on the mass hanger. Then VII, pull the hanger gently downwards and release to set into vertical oscillations. I determine and record the time T for 10 complete oscillations. S, evaluate and record the period T, capital T, for the oscillations, like the 10 complete oscillations, and T squared, period squared. Then SI, repeat the experiment or procedure for M equal to 70, 90, 110, and 130. Then SII, SII. In each case, determine and record L and T. L is the length, the new length when the mass is hanging on the mass hanger, mass of 50 gram, mass of 70 gram, mass of 90 gram, mass of 110 and 130. That's what that L stands for. And then T, small t, the time for 10 complete oscillation of each of the masses. Then SII, evaluate and record small e, that extension, capital T, that the period, and then period squared. Tabulate readings. Plot a graph of E, small e extension, on the vertical axis against T squared, that period squared, on the horizontal axis, starting both axes from 0, 0. Determine the slope S of the graph, that's the next question. The other one, evaluate K equal to 4 pi squared S, where S is the slope, taking pi as 22/7. Then the other one, it says state precautions. So let's go to the question. So these are the readings obtained for the experiment. The mass of the hanger used is 50.00 gram, which is uniform for all schools. Then our LO is 64.00. Our LO is 64.00. So our LO is 4.00 cm. Okay. The mass is slotted in 50, 70, 90, 110, and 130. Then the new length, when the mass was slotted in, when 50 gram was slotted in, the new length became 67.00. When 70 gram was hung on the mass hanger, the new length is 68.00. When 90 gram was hanging, the new length became 69.00. When 110 gram was hanging, the new length became 70.00. When 130 gram was hanging on the mass hanger, the new length became 71.50. We'll now go to the extension. How do we find the extension? The extension is the new length, L minus LO. L minus LO. So to get the extension for the 50 gram mass, that's going to be 67 minus 64, giving us 3.00. For the 90 gram mass, the extension is going to be 68 minus 64. 64 is constant. That is 4.00. For the 90 gram mass, the extension will be 69 minus 64. That gives us 5.00. For the 110 gram mass, the extension is going to be 70 minus 64. That gives us 6.00. For the 130 gram mass, the new length is going to be 71.50. The extension is going to be 71.50 minus 64. That gives us 7.500. So to get the extension, we subtract the new length when the mass is hanging. The various masses 50, 70, 90, 110, 130 are hanging on the spring. We subtract the value, the length is L, of course. We now do the operation L minus L0, where L0 is constant value for this experiment, 64 for this experiment. Then we now say the 50 gram mass into 10 vertical oscillations. We did each of them twice. The first one 11.40, second one 11.36. Averaging at the mean, which is T1 plus T2 over 2, gives us 11.38. We set the 70 gram mass into 10 oscillations, did it twice for accuracy, 11.50, 11.42. We took the average, that gave us 11.46. Using the 90 gram mass set into 10 vertical oscillation, we got 13.20 and 14.0. Adding the two, taking the average, we have 13.60. Then 110 gram mass, 17.90 for the first one, coincidence, 17.90, average 17.90. The 130 gram mass, when set into 10 vertical oscillation, gave us 19.00 for the first time, and then 18.60 for the second time, averaging giving us 18.80. Then to find our period is the average time over 10 over number of oscillation, T over 10. That where capital T is the period, where and small t is the average time, T1 plus T2 over 2. So dividing 11.38 by 10, we'll have 1.138. Dividing 11.46 by 10, we'll have 1.146. Dividing 13.360 by 10, we'll have 1.360. Dividing 17.90 by 10, we'll have 1.790. Dividing 1.80 by 10, we'll have 1.880. And so on. Then the next column is period squared. T squared. So we squared 1.138, we had 1.295. Squaring 1.4146, we have 1.313. Squaring 1.360, we have 1.850. Square 1.790, we had 3.204. Squaring 1.880, we had 3.534. So this is the table presented for this experiment. Then we're asked to plot a graph of extension, which starts from 3 and ends at 7.5. That is 3, 4, 5, 6, and 7.5. Extension on the vertical axis, and then period squared, the last column on the horizontal axis. We start from 1.295 and ends at 3.534, 1.295, 1.313, 1.850, 3.204, and then 3.534. So these are graph presented there. On the vertical axis, we have extension in cm. You look at the scale we chose. We chose 1 cm to present, that is 2 cm to present 1 unit. So each boss is 1, 2, 3, 4, 5, 6, 7, 8. So 1 cm, 2 cm, sorry, that is one boss to present, 2 cm present 1 unit. That one ball for 1 unit on the vertical axis, which is the E axis. Then on the horizontal axis, we now choose 2 cm, a boss is 2 cm to present 0.5 unit. 0.5, 1.0, 1.5, 2.0, 2.5, 3.0, 3.5, and so on. To know what one line represents on the vertical axis, I'll divide 1 by 10 lines. So one line here will be 0.1 unit. To know what one line represents here, I'll divide 0.5 by 10 lines. I have 0.05. So one line here is going to be 0.05. That means 2 lines will become 0.1. Then after putting the graph, we had a straight line graph. A straight line graph. And we'll have to take our best line for a perfect experiment. We observe that 2 points fell out of the graph due to experimental error, 2 points, and then 3 points are on the straight line. 1, as you can see there, 2, and then 3. So we took our slope using the first point there, and then the last point there. So let's go to the slope. So taking our slope, which is a change on E axis all over change on period square of period axis, we have 7.5 minus 5 all over 3.53 minus 1.85 cm for unit for the numerator and second squared for the denominator. Solving it out, we now had answer as slope as 1.488 cm per second squared, approximately 1.49 cm per second squared to 3 signal figures. The next question, we asked to evaluate k equal to 4 pi squared s. So we now have 4, pi is 22/7 squared, then s is our slope, which is 1.49. Solving this out, we obtained 59.9 centimeter per second squared as the value of our constant k. Then the next question is precautions. The precautions obtained the experiment. 1, I ensured that I avoided error due to parallels in reading the stopwatch. Number 2, I ensured that I displace the masses through a small amplitude or a small angle to avoid gyration. We go to BI, we are asked to state 2 objects or 2 bodies that can perform simple harmonic motion apart from the one given to us in the question, apart from the spiral spring. So example, swinging motion of a pendulum bulb. That is also an example of extension motion. Number 2, vertical displacement of a loaded test tube in water. That is a test tube loaded with less shots displaced in water will also undergo simple harmonic motion. BII says a student timed 15 oscillations of a loaded spring thrice and obtained 34.80 seconds, 36.00 seconds, and 33.75 seconds. Calculate the mean period of oscillations. We go to the solution. The time 34.80 as T1, T2 36.00, T3 at 37.75. We first of all find the mean time or the average time using the formula there, T1 plus T2 plus T3 over 3. Solving it out, we have that substituting 34.80 plus 36 plus 33.75 all over 3. Solving this out, we had The average time at 34.85 seconds. Then period is time over number of oscillation. When I use average time 34.85 seconds all over 15 because oscillation was done 15 times. We have 15 oscillations. So 34.85 over 15 gives us 32.32 seconds. So good luck. Always stay connected to this YouTube channel. Always tell your friends to subscribe, and also subscribe and learn something new every day. Thank you.